And so my name is Jon Bruner. I work on industrial and manufacturing strategy at Formlabs and lead up what we're doing to get 3D printing into more places, more critical places in manufacturing. So Formlabs, by the way, we make professional desktop 3D printers that are very capable and that you can use for a lot of applications, and I'll get into that a bit more in a little bit. But first, as Matt mentioned, this is the second time I've spoken here. The first time was almost 5 years ago in January of 2014. The trees on stage were a little bit more feeble at the time, and we lived in this really interesting period in the evolution of 3D printing that's quite different from what we're seeing today. This is a cover from Wired from 2012, and of course with the MakerBot on the cover and Brie Pettis, and of course MakerBot was purchased by Stratasys in 2013. There was this idea that was floating around that 3D printers were this catch-all solution to practically everything, and that a lot of consumers even would have 3D printers on their kitchen counters, and 3D printers would do in like Home Depot and UPS and Williams-Sonoma and everyone who made physical things, because you would just like churn out a thing from your printer. And indeed, this stimulated a lot of interest in 3D printing. These are the share prices of Stratasys and 3D Systems, the big publicly traded 3D printing companies. And as you can guess from any slide like this that ends precipitously in the middle of the graph, something dramatic happens. This is what it looked like immediately after I last spoke at Hardwired. So I hope that my timing's a little bit better this time. And so there was this realization that there was a bit of an overpromise. People weren't thinking very clearly about how 3D printing was going to really make a difference. And Wired kind of like walked back its ideas about 3D printers, and then we all went into a dark age of some sort. Yet, we are today with 3 3D printing unicorns. And no 3D printing unicorns existed at the top of the last hype cycle in 2014, so something is pretty different. I work for Formlabs, as I've mentioned a couple of times now. Also Carbon, which is based in California and does other kind of plastic 3D printing, and Desktop Metal, which is based outside of Boston, like Formlabs, and does metal 3D printing. So all of these companies are worth something above $1 billion now, and they're changing. They've approached this area in a way that's a bit different from the way that the sort of consumer hypey companies did 5 years ago. So this is our main product, the Form 2 3D printer. How many of you have operated a 3D printer before? Okay, so like a third or so. This works a bit differently from the more familiar 3D printers like the MakerBot. This is what's called stereolithography. So you take a liquid plastic resin and you cure it with a laser. It's like you've probably seen adhesives like this if you go to the dentist or something and you get a coating put on your teeth. The dentist puts on like orange goggles and shines a light in your mouth. This is the same idea, except you're using an ultraviolet laser that's controlled by a computer, and you're going layer by layer, and you're curing these materials. So let's take a look at sort of what's changing. One of the first things that's changed in the last few years is the variety of applications that you can approach with 3D printing now. And this really comes out of a lot of both careful technical advancement and careful thought about how 3D printing can solve specific problems within different industries. Formlabs now has 17 different materials. Some of them are like pretty finely sliced, but the upshot is that 3D printing can now be valuable and really accessible for applications all the way from digital dentistry like this. These are 3D printed surgical guides and models that are widely used in dental practices today, all the way to heavy industry. This is an automotive factory where, thinking back to Etienne's presentation a moment ago, you're using a 3D printed jig to handle specialized transmission parts on an automated line. So this is an aluminum base, and then this is a 3D printed jig on top of it. So you're able to advance the cycles in manufacturing much faster and be much more flexible in how you approach stuff. So let's dive into a few of these advances that have happened in the last few years. One of them is that the materials themselves, as I mentioned, have become much more capable. as direct use materials. So this is tough resin, and it can not only withstand some of the wear and tear of a factory, of like robots putting parts into it, of getting passed into a CNC lathe. It can also withstand even the chemical conditions inside these machines, which are just like exploding with coolant all the time and getting kind of exposed to a lot of not great stuff on the factory floor. But perhaps even more critical was this realization that 3D printing isn't always going to be about direct printing an end-use product. That there are a lot of products will always have to be made with a variety of manufacturing processes, a variety of fabrication techniques, and that 3D printing can fit in and make these often quite difficult manufacturing processes much easier and add a lot of value. So this is a process that we developed for creating custom earbuds. You start with a scan of your ear. There are 3D scanners that go inside your mouth and inside your ears now. It takes a few seconds. You got a 3D scan of the topology of your ear canal. You import it into software. You design a custom earbud. But then instead of 3D printing the earbud, which is tricky because not a lot of 3D printing materials are biocompatible and is a little expensive, what you do instead is you 3D print a mold on like what you see on the left out of a standard 3D printing material, and you cast silicone into it, medical grade silicone, and then you break the mold off, you add a medical grade lacquer, and you finish the product like that. The whole thing costs like $3, and it's faster and easier, and you get to work with silicone, which is a completely dependable material that you're used to already. Injection molding, of course, is like the way that almost all of the plastic objects that you encounter on a regular basis are formed. You take a mold and you shoot hot plastic into it, and then you open the mold and the plastic comes out. And injection molding is, it's got kind of the opposite economics of 3D printing. With injection molding, it's extremely costly to create the mold, to create the tool. It can cost anywhere from like $5,000 to $500,000 to cut an injection molding tool. But then everything that pops out of the mold is extremely cheap, like fractions of cents. 3D printing works the other way. There's no upfront fixed cost, but then on the margin, the parts are a lot more expensive than injection molding. Now you can kind of blend these, and you can actually 3D print injection molds. They don't perform just like steel molds, but they're this remarkable bridge that makes it possible to do a lot of new things at new scales that weren't feasible if you're just like cutting injection molds out of hard steel. So this is a high temperature resin, high temperature 3D printing material that can withstand temperatures up to 289 degrees Celsius, which is ample for doing sort of low pressure, short run injection molding. And in fact, you can even be more dramatic about it, and you can cast soft metals like pewter into a 3D printed mold. And you can do really cool things like this, where you design a shape which would be difficult to sort of fabricate otherwise, difficult to work out by hand, difficult to machine in steel in order to make a mold. You can 3D print it instead and get this geometric freedom, and then pour metal into the mold, into the 3D printed plastic. So this is a kind of capability that you just didn't see in any kind of accessible 3D printer until a couple of years ago. This is another one that's really critical for a lot of industries, but especially for jewelry, and I have some cool pieces up here that you can all touch after the presentation. This is an illustration of investment casting, which is how a lot of metal parts are made, especially really fine small metal parts. Basically, you take a form, which is what you see on the left in purple, and you immerse it in a ceramic slurry, and then put the whole thing in an oven and fire it on a particular curve. You fuse the ceramic slurry into a solid, and you melt the form out of it, and now you have a cavity that you can pour liquid metal into and create an interesting shape. So in this case, and here's an illustration of that. So you take the 3D printed form and you immerse it in the ceramic, you fire it in an oven, and then you can finish the piece. What you wind up being able to do is create entirely new kinds of products, things that you wouldn't have been able to, shapes that you wouldn't have been able to produce by hand or by, again, machining or molding in other ways. What you wind up with as well is an end product that was made with 3D printing, but which has no 3D printed material in it whatsoever. So this is a piece of jewelry, which would be familiar to anyone who's bought jewelry that's made any other way. We even have new materials that 3D printed ceramic, which is what this is, and I have a few pieces again that you can touch after the presentation. Nothing is as mind-blowing to hold in your hand as 3D printed ceramic, especially like a 3D printed ceramic lattice, because you're just not used to the idea that ceramic can be made in shapes like this. You wouldn't be able to machine or mold a really fine lattice like this. This is a material that's a ceramic powder suspended in a liquid plastic matrix. You cure the ceramic and liquid plastic in a 3D printer, and then you take it out and you fire it in an oven. It burns out the plastic and it sinters the ceramic together. This is the stage. This is like straight off the 3D printer on the left. This is after firing, and then this is after glazing. So the capabilities of 3D printed ceramic go, again, way beyond what you've ever seen before in 3D printing. It's gorgeous. These are designs by a really cool design firm in Cambridge called Nervous System. And it's also highly practical. You can do stuff with these 3D printed parts industrially and artistically that you couldn't do with 3D printing before. You can even use this. This is a gas nozzle that you can use at extremely high temperatures because it's just ceramic, and you're able to enjoy this geometric freedom to design the part in the way that you want without the limits of conventional manufacturing. The next huge advancement that you're going to see is the arrival of selective laser sintering in the kind of accessible 3D printing world. These machines usually cost north of $100,000, but this is our second main 3D printer that's coming out next year, shipping next year, called the Fuse 1, and it's $10,000. So there's this enormous price pressure downward and an emphasis on ease of use that makes it possible for a lot of different people from different backgrounds to use these processes. In selective laser sintering, what you have is a bed that you spread a thin layer of powder over. In this case, this is nylon plastic. It's a great engineering plastic, PA12. And so you spread a very thin layer of this nylon powder over the bed, and then you use a laser to sinter, to fuse the nylon together in a particular shape. That's one layer of your part. You spread more powder over on top of it, and you fuse that layer as well with the laser. You can make all sorts of things with selective laser sintering. One of the drawbacks of other types of 3D printing processes is that they tend to be fragile, but these are very strong parts, and you get complete geometric freedom because the unfused powder supports the part that you're fusing in the printer. So there's no limitation as far as support structures or difficult geometries that you have to kind of consider as you're designing. You can even design things that are that move, that are mechanical assemblies that work straight off the printer. I'll show you one of those in a second. You can pack these parts extremely efficiently, and that makes a really big difference for manufacturers as well. So consider this bike pedal, which is a real working bike pedal that a colleague of mine rode to work for 6 months. And you can print a lot of them at once in the build chamber because, again, it's supported, all of these parts are supported by the unfused powder around them. So this really transforms the capabilities of manufacturing, of additive manufacturing, of 3D printing commercially. This is possibly the coolest thing that's come out of this printer so far. This is, again, a design from Nervous System, the firm I mentioned in Cambridge. And it's a dress made of 3D printed chainmail. So this is nylon plastic. It's made of 11,000 separate links, each of which moves separately from the others. And it's much larger than the build volume of the printer, and so it was printed like this. There was a physics simulation that took this nylon, this chainmail dress with separate links, and you imagine it dropping into the build chamber like this, and then you print it in the 3D printer in that shape. So it comes out like wadded up, and you pull it out of the printer, and you kind of flick it off, and all of a sudden there's like this dress that you're holding. This is really magic, and this gets to the freedom and the flexibility of 3D printing, it's not just kind of the ability to do things, to do mass customization or whatever. It's also just this incredible freedom to design the stuff that you want to design. So you're going to see products changing because there are now these really capable 3D printing processes and materials that you can use to create the things you want to create. So to go back to these 3 companies that I mentioned that are the 3D printing unicorns at the moment, Formlabs is a bit different from the other 2. Carbon and Desktop Metal are both exerting some downward price pressure on the industry, which is good, but Formlabs is focused entirely on producing 3D printers that are not only inexpensive, but also really easy for the end user to use. And this is important because the same printer can then become the kind of universal 3D printing platform for every step of the product development lifecycle, from an individual engineer or designer with a single 3D printer to a small run prototyping operation to a full manufacturing operation. This is the Form cell. It's an automation cell that contains between 5 and 10 Form 2 3D printers, and there's an arm that comes and changes out the build platforms and does a little bit of post-processing on them. And so our idea is that just as in the 1960s and 70s, computing was monolithic, you had these giant mainframes, but then it became clear that there were these advantages to distributing computing and giving everyone access to computing and doing computing in all sorts of different places. We see an opportunity to do the same thing with 3D printing. It's just as capable, but it's much, much more accessible. So this is an industrial 3D printer that costs like $300,000, and these are desktop 3D printers that cost $3,300, and that do almost as much as the printer on the left. And you can buy, a lot of these printers, of these desktop printers, for the cost of a single industrial machine. For one of these really beautiful industrial machines from Carbon, it costs about $160,000 to rent one for 3 years. And for that amount of money, you can buy 50 desktop 3D printers that really transform what you're doing, because not only can you produce on 50 printers in parallel and get just tremendous output, but you can also put them all over your company and encourage people to sort of innovate with them and encourage people to really embed 3D printing in the things that they're designing and developing. So, thank you all so much. I'd be glad to take questions.
Actually, that last bit in particular was, the whole thing was super interesting, but that last bit I didn't realize you can actually parallel process. There's a concept of distributed printing.
Yeah, and it's incredibly powerful when, so that there are a couple of layers of management that you can do. One is, managing a bunch of different printers in parallel. Another is that if you think about a lot of uses of 3D printing, you're using much less than the full build volume on each part. For instance, if you're a dental lab and you're making mouth guards or aligners or something like that, each part, you can fit 16 of these parts or something on a single build platform. So you can further parallelize it by manufacturing, 16 different parts simultaneously in an individual printer. So there's a lot of room to automate that kind of management process.
In the 3D printing wars, how much of the competitive advantage is software as opposed to the actual printer?
That's a good question. Some of the 3D printing companies are coming out with their own generative design software, which they see as a major advantage. We don't have that at the moment, but they're thinking that if you control the output and you know something about how the output of the process works, you can sort of feed it into the algorithm that can do generative design. In our case, we have a web platform that tracks printer usage, that monitors wear on the consumables, that sort of reminds you when you need to replace things, and that helps you manage your fleet of printers. And that's extremely valuable as well.
Great. Over there.
We have seen, as you mentioned in the Wired magazine, that back in 2014 there was a buzz, and there are a lot of consumer products that we buy today, and none of them actually come with a 3D printer specification. So something like I broke something around the clip in the dustbin, and the clip in the dustbin can really be printed at home. I could make it in MakerBot, but the 3D printed design of that is not really accessible. So is Formlabs in any form tying up with the manufacturer to actually produce products or produce 3D printed designs for the product so that you could buy a replacement part on demand and not have to, just purchase a new product?
Yeah, so you make a very good point, and this was one of the things that really sank that initial burst of energy in consumer 3D printing, is that like a lot of people bought a desktop 3D printer and brought it home, and they were like, great, I'm going to create these amazing things and really realize my ideas, or especially my kid is really going to like, come up with amazing ideas and 3D print them and be very creative. And then it turns out that your kid has to learn parametric solid modeling, and that isn't very easy. And it remains the fact that that CAD software is still often one of the more difficult parts in the process of designing and fabricating something if you're a consumer. So there are a few approaches. I mean, Formlabs owns Pinterest, which is one of the 3D printed design marketplaces. There's also like Thingiverse, which is owned by MakerBot inside Stratasys. There are a few others as well. There are a few attempts to create consumer-friendly CAD software. It's an area with a lot of investment currently and interest. Formlabs does not have, we have a software called Preform that's for preparing your designs for printing. And we try to make that as easy as possible because it is very important. A lot of other 3D printers require a lot of technical expertise and kind of like doing this print preparation. Ours is really like one button to print. But beyond that, we aren't developing our own CAD software. I'm gonna make Jack run.
You mentioned like plastic and ceramic and metal. What material are you most excited about that's either now able to be printed with or is coming in the near future?
Well, I think so. Probably nylon plastic. I mean, it changes a lot of the limitations that you experience with even really good other kinds of plastic in 3D printing. It's like, it's so much stronger than a lot of other sort of acrylic or PLA-based plastics, and the fact that you can print it in an SLS machine without supports really changes a lot of the limitations as well. I have a part here that you can all see afterwards. These are like interlocking links that came off the 3D printer like this. You can imagine a lot changing in the way that things are designed if they're 3D printed and if they're designed for 3D printing from the beginning.
That question made me think about another question about if you have this flexibility to start thinking of new materials that you want to be able to print with, where does sustainability come into that? Because printing lots more plastic things isn't good for us overall.
Yeah, that's an excellent question. 3D printing at the moment is mixed on sustainability. On the one hand, when you 3D print something, in theory, you can 3D print exactly the part that you need. And so there's less waste in the manufacturing process, and hopefully you're making better products that are less wasteful as well. In practice, that's not often the case. Usually you're printing a lot of different variations of something, you're printing things with support structures, which you're throwing away, and a lot of 3D printing plastics are not recyclable. Some of the thermoplastics are, but the thermoset plastics, like the liquid resins, are not generally recyclable. So I think that it's probably going to be approached through a combination of material development, like materials that can be more sustainable, and improved design that mean that you waste less in the fabrication process. But that's a super important question, and it's not ideal right now.
So if a new material comes along, right, do I need to buy a new printer, or can I reprogram the one I have?
Do you need to buy a new 3D printer, or can you reprogram the 3D printer that you have?
Yes.
How old is your 3D printer?
Well, let's say I were to buy it today.
Yeah.
I would imagine that I'd have to go deep into the software and control the laser and stuff like that. So is it possible to get like an upgrade, or how would that process work?
Yeah, so I mean, we routinely upgrade the firmware in our printers over the air, and it improves print performance. I mean, it improves the quality of the parts that come off. So software upgrades are part of the way that we think about these printers. There's also an open mode and an API that you can sort of use to crack into some of the lower level stuff in the printer. In this case, the chemistry of these is a little bit more complex than kind of melting a thermoplastic with an extruder. And so the manufacturer's settings for printing are tuned to the quality of the materials. And you need to change a lot of different things if you want to sort of experiment it with yourself. But the broader question, sort of how much are these printers advancing, and how long will they last? I think they actually will last for quite a while. A lot of the improvements are coming on the materials side, and you can do a lot of upgrades through software alone. So you're not exactly in a race like with computers in the 90s, where you're just like building a new printer that has a more powerful laser every year. That's not really where it's going. It really is in the software.
How does the distributed printing model affect the Venn diagram of speed, quality, cost, size?
So distributed 3D printing model, how does that affect everything, basically? That's a good question. So we have a lot of our users are using Form 2s to do kind of like marketplace, 3D printing marketplace work. You can go on 3D hubs and order parts through kind of a distributed network of people who own 3D printers. I think if you're thinking of distributed manufacturing everywhere, that favors the desktop model rather than the industrial model, because you can truly distribute them much, much more. And a critical consideration for the industrial models is that you generally need a really highly trained workforce to operate them, whereas these are completely accessible to people with just a little bit of training. So yeah, that's my initial thought on your question. But I'll think about this and see if I come up with something else.
One last one over there.
You have a question? No. Yes. I think what you guys are doing is awesome.
Thanks.
Has anything changed in the past 5 to 10 years that have driven the prices of industrial level laser sintering machines? I was looking at the Opjet Vera was $200,000 10 years ago, that have enabled the $10,000 laser sintering machine.
Yeah, so the question is, what's really changed in the underlying ecosystem to make it possible to bring these things down by more than an order of magnitude? Part of it is the same story as with any piece of hardware. You have a lot of embedded computing, you have other kinds of electronics, they're all solid state now. It becomes easier to control things, it becomes easier to develop a product, prototype it, send it out to be manufactured by a contract manufacturer, and then there's more stuff that you can do with software. In the case of this one, actually, of the Form 2, which brought the price of SLA down from $35,000 at minimum to $3,500, one of the advances was that Sony had spent a fortune developing the 405 nanometer laser for the Blu-ray. And this really drove the price of blue lasers down. Previously, they were prohibitive. Now you can have them in a 3D printer like this. In the case of the Fuse, and in this case too, it also is just a matter of rethinking it completely as an inexpensive, accessible machine, which the incumbent manufacturers had just never tried to do. No one who's sitting on a $200,000 machine that's selling well is going to say, let's devote all of our engineers to making a $10,000 machine with all the same capabilities that will crush our existing product line. So.
All right.